Evaluation of saliency-based explainability methods. Saliency-based explainability methods, in the case of classification, are a group of XAI methods that aim to explain convolutional neural networks by highlighting regions of the image that most contribute towards the classification. They use some form of modified gradients or attribution backpropagation. The examples include GradCam, FullGrad, excitation backprop, deep lift, and several others. An example image is shown and the corresponding GradCam maps for the cat and the dog classes are shown. There are no metric to evaluate the efficacy of XAI methods, and we need qualitative and not quantitative metrics. Most prior work that has focused on the evaluation of saliency-based methods are quantitative tests. So we have a solution in the form of human subject experiments. We believe that humans can be the best judge for these saliency-based methods, as the methods need to be explainable for humans. The only caveat being that explainability methods need to be considered individually, as newer methods would arrive and we would want to test or judge the methods as well. The saliency-based methods that we have considered are GradCam, excitation backprop, FullGrad, which generate broad region-level saliency maps. Then saliency, SmoothGrad, integrated gradients, the SmoothGrad variant of integrated gradient, deep lift, and GradShap, which all generate pixel-level saliency maps. We have used the VGG16 model on the dataset animals with attributes, that is AWA2 with a subset of 20 classes or animals, which we trained to an accuracy of 96.6%. We have also used the Caltech UCST Birds 200 dataset, which is a dataset of 200 species of birds, which was trained to an accuracy of 73%. We conducted the human subject experiments in the form of surveys. The goal of the first experiment was to measure the predictability and class discriminativeness of the explainability methods. To do this, we asked the human subjects to predict the ground truth class's saliency map when shown the saliency maps for the top 4 classes without the labels. A demonstration for the survey application is shown. We use the AWA2 dataset for this experiment, and we measure the accuracy of the subject in correctly predicting the class as the score. Ideally, the saliency map of the ground truth class would either demarcate the object of interest in the image from the background or highlight obvious discriminating regions. The second experiment's goal was to measure the reliability of the methods. Justifiable explanations, even for misclassifications, make the method reliable. To do this, we show the participants the explanations for the misclassified images, misclassified, that is predicted class, versus the true class saliency maps, and ask them to rate on a Likert scale the degree to which they agree that the explanations are justified for the misclassified image. The Likert scale is shown in the survey example. Strongly disagree corresponds to 1, disagree corresponds to the value 2, and so on, and strongly agree corresponds to the value 5. We measure the mean of the Likert values as the score. The goal of the third experiment was to measure the consistency of the methods. By consistency, we mean that the explanation method for similar images would highlight similar regions of the image or having same patterns within the image. We show the users several saliency maps of correctly predicted images belonging to the same class. We use the CUP dataset for this experiment. We asked the participant to rate on a Likert scale the degree to which they agree that the saliency maps of different images of the bird focuses on the same or similar parts of the bird. This experiment is particularly beneficial in the case of the fine-grained image classification task. We show the accuracies for the task outlined in experiment number 1 that measures predictability. GradCam has the highest accuracy of 43.9% among all the XAI methods. Excitation backprop and saliency followed this with accuracies of 35.8% and 31.7% respectively. Here we note that GradCam has an accuracy of 43.9% despite no context being provided to the users. We also note that both GradCam and excitation backprop highlight large regions of the image where boundaries may not be well demarcated, but the saliency maps may still be very class discriminative. The table shows the ranks of the XAI methods based on the mean values on the Likert scale. For experiment 2, gradient sharp and full grad have the highest mean, 3.38 and 3.36 respectively. Full grad has a Likert mean value of 4.51 in experiment number 3. Excitation backprop and gradient sharp being the next highest at 3.92 and 3.9 respectively. This implies that there is a near unanimous consensus that the explanations provided by Fulgrad are consistent for the VGG16 model trained on the CUP 200 dataset. The pictures show the heat map of the mean accuracies in experiment 1 for the methods against each class on the left. We want to bring attention to the fact that some classes exhibit better accuracy overall, indicated by a lighter tone in its column relative to other classes like giant panda, gorilla, and tiger. The opposite can be seen in the cases of humpback whale, polar bear, rhinoceros, bear, which have relatively darker columns. This similar phenomenon is observed in the left picture, which shows the heat map of the mean Likert values in experiment number 2. For the methods against each class, the classes gorilla and tiger are relatively lighter, contrasted with the classes humpback whale, pig, and rhinoceros, which are relatively darker, as seen by their corresponding columns. This phenomenon suggests that explainability differ among individual classes. To summarize, we gauge the effectiveness of saliency-based XAI methods. We do this by designing 3 human-subject experiments to capture desirable qualities of XAI methods like predictability, reliability, and consistency. We find that gradient sharp and full grad are effective and also that full grad is rated highly consistent. As suggested by the experiments, a human-centric approach to XAI might assist to bridge the vast gap that exists between the explanations and their utility. Thank you.